In this module, we're going to talk about how two types of bonds, ionic and covalent bonds, form. What causes them to come about? Well, in order to understand this, we're going to need to know something called the octet rule. And this is the octet rule, and it would be a good idea to memorize it. Not verbatim, but the general idea. So what happens when chemistry happens, basically, is that atoms either gain, lose, or share their valence electrons, their outermost electrons, so that they have the same number of electrons as the nearest noble gas. And when I say nearest, I mean with the closest atomic number. So if we look at a periodic table right here, so these are the noble gases, and let's say calcium, okay, what's it going to do when it reacts? Well, it has 20 electrons. The nearest noble gas to that nearest atomic number is argon with 18 electrons, not krypton, which has 36, right? So calcium will tend to lose 2 electrons so that it has the same number of electrons and consequently the same electron configuration as argon. So if calcium, which has 20 protons and 20 electrons when it's neutral, loses 2 electrons, it will have, to be like argon, it will have a positive 2 charge. On the other hand, if sulfur reacts, it's going to tend to gain 2 electrons so that it can be like the nearest noble gas, have the same number of electrons, argon, which has 18. So sulfur would gain 2 electrons and it would have a negative 2 charge. It would make an anion. That's the octet rule. Now, ionic compounds. Ionic compounds, we've seen, consist of a cation and an anion, something with a positive charge and something with a negative charge. Now, the reason why these ionic compounds form and how they can exist and why they're stable, when we say stable, we mean low in energy, is described by something called Coulomb's law. This says that the energy of interaction, or the ionic energy in this case, is equal to 2.31 times 10 to the minus 19th joules nanometers times Q1, Q2 over R. Q1 and Q2 are the charges on the ions, and it's either going to be plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, maybe plus 4, minus 4 in weird cases. R is the distance between the centers of the two nuclei. The units of charge, Q, usually are coulombs, but that's taken into account in this number right here. So these numbers here are unitless, and they're positive or negative integers. This R is going to be the distance between the nuclei, and it's going to be in nanometers. That's taken into account in this number here. Memorize this equation. Now here's how you might use it. Okay, if we wanted to find the ionic energy, the energy of interaction between a calcium ion and a bromide ion, we would use that, and you'd have to know the distance between them. Okay, at this point I'm going to tell you what it is. We're going to take it as 2.94 angstroms. Now remember, an angstrom is 1 times 10 to the minus 10th meters. We need our distance, our R, to be in nanometers. See this distance right here? That's going to be our R in Coulomb's law. Q1 and Q2 are going to be the charges on the calcium ion and the bromide ion. Well, you know that calcium, it's not one of the metals that can have a Roman numeral, so that it means it only forms 1 charge. It's an alkaline earth metal, forms a plus 2 charge. Bromide forms a negative 1 charge, and we've just seen why that is, so that they can have the same number of electrons as the nearest noble gas. So the charge on the calcium is plus 2, the charge on the bromide is minus 1, the distance between them is 0.294 nanometers. Okay, 2.94 angstroms. An angstrom is 1 times 10 to the minus 10th meters. A nanometer is bigger, and then 10 to the minus 9th. So 1 order of magnitude bigger, so it's 0.294. Plugging in, we get negative 1.57 times 10 to the minus 18th joules. That negative means it's an attractive interaction. If we got a positive number, how would we do that? Well, if both of these were positive, or if both were negative. If we had an anion and an anion, or a cation and a cation. The energy of interaction, the Coulombic energy, would be positive, and that's repulsive, not stable. All right, so now a covalent bond forms for basically the same reason as an ionic bond. It's trying to lower the energy of the system, the atoms, right? But here, let's look at two hydrogen atoms. And this graph, we're kind of going to read it kind of strangely. We're going to start from the right and go this way. So imagine two neutral hydrogen atoms infinitely far away from each other. And we start bringing them closer and closer together. Well, the energy of these two hydrogen atoms each with one electron and one proton is, we're going to call their energy, pretty close to zero, just a little bit below zero. As we bring them closer and closer together, what's going to happen is the electron from this atom is going to see the proton from this atom. It's going to feel the effect through Coulomb's law, and amongst other things. The electron here is going to feel the proton here, and they're going to lower the energy. This interaction will lower the energy of these two atoms, and the energy is going to go down. This axis, by the way, is potential energy, and it's going to keep on going down until it reaches some minimum. It ends up, that's for hydrogen, is 0.074 nanometers. Now, if we keep pushing these two guys closer together, what happens is now the protons start feeling each other. They repel each other, and the energy starts going up, and it's repulsive, and it gets shoots up towards infinity there, really. So there's some distance where this energy is at its minimum, and that's going to be what we call the average bond length for hydrogen, or for whatever molecule it is. Now, when we have a covalent bond, but the two atoms are different from each other, such as in hydrogen fluoride or hydrofluoric acid, the two atoms don't necessarily have the same attraction for the other electron, or for the electrons between them. When that happens, we form what's called a polar covalent bond. And a polar covalent bond means that the molecule itself is what we call polar. What does polar mean? Well, it means that one end has a positive charge, the other has a negative charge. And the atom that has a stronger pull on the electrons will have the negative charge, because it's pulling more electrons, or electron density, towards itself, and away from the other atom, which leaves its proton or protons slightly exposed, having a positive charge. When that's the case, one of the effects of having these poles, positive and negative poles, in this molecule is that when we put them into a magnetic field or an electric field, either one, we will see an effect. We'll have attractive or repulsive interactions. Let's say we put them between two charged metal plates, like here. And if this plate is negatively charged and this is positively charged, what's going to happen is these molecules are going to flip around and orient themselves so that the opposite charges are close to each other. The positive part of the molecule points towards the negative metal plate, and vice versa over here. Up here, before we turned on the charge, they were just oriented in any old direction, random directions.